All right, guys, today we are going to go over limiting and excess reactants. We're going to go through conceptually what they mean, and then we will also do problems involving limiting and excess. All right, when we talk about a limiting reactant is the substance that runs out first in a reaction. The excess reactant is the substance that is not completely used up or consumed in the reaction. All right, up until this point, we have assumed that all of the reactants run out at the same time, but that's not always necessarily true. Sometimes we run out of one ingredient before the other, and as soon as we run out of one ingredient, the whole reaction stops and we stop producing product. We're going to look at a model first for a really simple reaction. So here I have H2 and it's drawn, my molecules are drawn here with the closed dots, reacting with O2, the open dots, in order to form H2O. So we are going to look at this and we are going to determine from this picture which is our limiting reactant and which is our excess. All right, this number out front, the coefficient, tells me that it takes 2 hydrogen molecules and 1 oxygen molecule to produce 2 water molecules. Water consists of 2 H's bonded to 1 O. If I take 2 hydrogen molecules and 1 oxygen molecule, I can make 2 water molecules. Now, there's still extra of the hydrogen and oxygen as reactants, so I can keep going. I can make more water. I'm going to take 2 hydrogens and 1 oxygen, and I can make 2 more water molecules. At this point, I can no longer make water molecules because I've run out of the hydrogen. There's no H2 remaining. So if I look here, there is an oxygen molecule remaining. So even though that oxygen molecule is there and unreacted, it will not produce water because there's simply not enough hydrogen. As soon as you run out of one ingredient, you stop making product. In this case, we would say that hydrogen is our limiting reactant and oxygen is our excess reactant. All right, let's take a look at another example, and this time we are going to use ham sandwiches as an analogy. We are used to cooking, we understand how ingredients work and how recipes work, so this is going to show us how to set up the problem mathematically once we transition to looking at chemical reactions. My ham sandwich recipe is as follows. 2 pieces of bread plus 3 pieces of ham plus 1 piece of cheese will produce 1 sandwich. I'm going to follow that recipe, and I want to know how many sandwiches can be made from 146 pieces of bread and 273 pieces of ham. Although a lot of us can pick up our calculators and plug this in, we need to be able to set this up with dimensional analysis. We need to be able to show our work and the cancellation of units. So I would set this problem up like every other Stoich problem we've done as examples up to this point. Identify the substances that you care about the amount of. I have 146 pieces of bread, so I am going to write that underneath the bread in my balanced equation. I have 273 pieces of ham, so I'm going to write that value underneath the ham in my balanced equation. Once I have identified what the numbers represent, I then want to identify what is my ultimate goal. What am I trying to find in this problem? And it's asking me how many sandwiches. The sandwiches are my end point. What we're going to do is we're going to focus on one ingredient at a time. So I'm going to focus on the bread first. And I'm going to figure out, if I have 146 pieces of bread, how many sandwiches can I produce? So I'm going to start with the number of pieces of bread. And according to my recipe, I can see that there's a 2-to-1 ratio between the bread and the sandwiches. So I'm going to put 2 pieces of bread on the bottom and 1 sandwich on the top. I'm going to put 2 pieces of bread on the bottom and 1 sandwich on the top. That way my bread cancels out and I can solve. If I have 146 pieces of bread, I would be able to make 73 sandwiches. But if the ham runs out first, I'm never going to be able to make 73. So what we're going to do is a second problem, and this time we are going to focus on the ham. And we are going to figure out how many sandwiches we can make with 273 pieces of ham. I'm going to multiply, and now my ham and my sandwiches are a 3-to-1 ratio according to the balanced equation. For every 3 pieces of ham, I produce 1 sandwich. When I do the math, I find that I can produce 91 sandwiches with 273 pieces of ham. Now, I'm not going to be able to make both 73 sandwiches and 91 sandwiches, but I know that I will only be able to make 73, and I know that because the bread is going to run out first. Whichever ingredient runs out first is the one that is going to determine how much product or how many sandwiches you can make. All right, let's look at an example that uses actual chemicals. So even though we're transitioning to a chemical equation here, the chemical equation is no different than the recipe that we used for our ham sandwiches. So we are going to approach the problem the exact same way. First, I'm going to start by identifying what each number represents. 5 grams applies to the H2, so I'm going to write it underneath the H2 in the balanced equation. 9.5 grams applies to the N2, so I'm going to write it under the N2 in the balanced equation. This time the question is asking me how many grams of NH3 can be produced. That means that grams of NH3 is my endpoint or my ultimate goal in this problem. Now, it is tempting to assume that hydrogen is the limiting reactant because there's 5 grams of it, which is less than the 9.5 grams that we have of nitrogen. But this is not a true statement. We can't assume that the hydrogen is the limiting just because there's less grams. This is for 2 reasons. First of all, according to the balanced equation, the hydrogen and the nitrogen are not consumed at the same rate. It takes 3 hydrogens for every 1 nitrogen according to this balanced equation. The second reason is because the molar mass of hydrogen and nitrogen are very different. So if I have 5 grams of hydrogen and 5 grams of nitrogen, remember that is not an equivalent number of moles. So for those 2 reasons, we cannot just assume that hydrogen is the limiting because there's less of it. Instead, we're going to have to do our stoichiometry and set up a problem. I am going to start by focusing on just one ingredient. I'm going to start by focusing on the H2, and I'm going to figure out if I use all 5 grams of H2, how many grams of NH3 can I produce? I can use stoichiometry and dimensional analysis to do this. I'm going to start with the 5 grams of H2, and I would like to use the 3:2 ratio that's in the balanced equation, but I can only use that when I'm in moles. So I'm going to go to the periodic table and find the molar mass of H2. There are 2.02 grams of H2 in 1 mole of H2. Now that I'm in moles, now I'm ready to use the mole ratio. The balanced equation tells me that for every 3 moles of H2, I produce 2 moles of NH3. Since the problem asks for grams, I now need to convert my moles of NH3 into grams of NH3 using the molar mass from the periodic table. I'm going to add up 1 N and 3 H's to get 17.03 grams. Now I can solve by multiplying across the top, multiplying across the bottom, and dividing my top by my bottom. When I do that, I get 28.1 grams of NH3. Now, this is not necessarily my answer. This is how many grams of product I will make if I use all 5 grams of H2. But it is possible that the N2 could run out first and therefore stop the production of NH3. In order to determine which reactant runs out first, I'm now going to check the nitrogen. I'm now going to do a second problem in which I start with nitrogen and determine how many grams of NH3 I can produce if I use all 9.5 grams of nitrogen. So I'd like to use the 1:2 mole ratio, but I first have to convert my grams into moles. I can do this by adding up N2 on the periodic table, and I find that 28.02 grams is equivalent to 1 mole. Now that I'm in moles, I'm ready to use my mole ratio, and for every 1 mole of N2, I will produce 2 moles of NH3. I need to make sure that I go to grams of NH3, just like I did in the last problem. You need to make sure that both problems end with the same substance and the same unit. So I'm going to convert my moles of NH3 to grams of NH3 using the molar mass. When I do that, I find that I can make 11.5 grams of NH3 if I use all 9.5 grams of nitrogen. Now, remember that the limiting reactant is going to stop the reaction. As soon as we run out of limiting reactant, we stop producing product. Therefore, the lesser amount of product is going to be the correct amount. I will never be able to produce 28.1 grams of NH3. All right, I know that 11.5 grams of NH3 is the amount of product that I'm going to make, and I answered the question. But it's important that we identify what the limiting reactant was. Remember that the limiting needs to be a reactant, and therefore it is the starting material that produced the lesser quantity of product. My limiting reactant in this case was the N2, and the excess reactant was the H2. If I wanted to calculate the amount of H2 that was left over, I could do that through another stoichiometry problem. Once you determine the limiting reactant, you'd want to start every subsequent problem with the limiting reactant. So we could determine how much excess we have if we started with the limiting, which is N2, and calculated how many grams of H2 we need to fully react. The difference between that and the 5 grams we started with would give us the amount of excess remaining. Let's do one more problem together. This time I have magnesium reacting with hydrochloric acid to produce MgCl2 and H2. I want to know what is the limiting reactant when 0.95 grams of Mg reacts with 10 milliliters of 1.5 molar HCl. I'm going to start this problem the same way I've started every problem so far, and I'm going to identify what substance the numbers belong to. First number I encounter is 0.95 grams of Mg, so I'm going to write it underneath the Mg in the balanced equation. I also know that I have 10 milliliters of 1.5 molar HCl. Under the HCl, I'm going to write the molarity, and I'm going to write the milliliters. When I have molarity, I know I'm dealing with a solution, and the equation for molarity is molarity equals moles over liters. So I am going to need to use that equation in this problem. Before we go any further, we need to identify the endpoint, and the endpoint here is just asking what is the limiting reactant. If it does not specify what product it's looking for, you can pick either product. You could calculate the amount of MgCl2 produced from both reactants, or you could calculate the amount of H2 produced from both reactants. It does not matter as long as you pick the same product for both problems so that you can directly compare the answer. It's important to identify my endpoint, and my endpoint is asking what is the limiting reactant. It does not specify what product it wants us to find, and in that case, you may choose either product, because remember that the limiting reactant will stop the production of all products as soon as it runs out. I could pick to calculate the amount of MgCl2 produced by both reactants, or I could calculate the amount of H2 produced from both of my reactants. It does not matter, you will find the limiting reactant either way as long as you choose the same product and the same unit for both of your problems. Now, that being said, we can often save ourselves some time if we read the next part of the problem. The next part of the problem is asking me how many grams of MgCl2 will be produced, so I'm going to choose to find my amount of MgCl2 in gram. Just like the previous problem, I am going to start with one of my reactants, and I'm going to determine how much of the MgCl2 I can produce if I use all of that reactant. The first step is to go to the periodic table and determine the molar mass of Mg so that I convert my grams of Mg into moles of Mg. Now that I have moles of Mg, I'm ready to use the mole ratio from my balanced equation. The mole ratio between my Mg and my MgCl2 is a 1:1. So 1 mole of Mg will produce 1 mole of MgCl2. Remember that my end goal here is to get grams of MgCl2, so I'm going to go one step further and convert my moles of MgCl2 into grams of MgCl2 using the periodic table. When I add up 1 Mg and 2 Cl's, I get a molar mass of 95.21, and now I'm ready to solve the problem. I'm going to multiply across the top, multiply across the bottom, divide my top by my bottom, and I end up with 3.72 grams of MgCl2. This is the amount that I will make if I use all of the magnesium, but it's possible that the HCl could run out first. So I now need to set up the second problem to determine how much MgCl2 I'll make if I use all of the HCl. Notice that this problem does not start with grams like the previous. Instead, I have a molarity and I have milliliters. Remember that my equation molarity equals moles over liters is going to be helpful here. I have my molarity. I don't have liters, but I can easily convert my milliliters into liters by dividing by 1,000. That gives me 0.01 liters. Now I have liters and I have molarity, which means that I can solve for my moles. As soon as I have moles, I'm ready to set up the stoichiometry problem. I'm going to substitute 1.5 in for my molarity. I don't know my moles, so I'm going to call that X, and my liters are 0.01. When I solve this, I get 0.15, but it's important to remember what unit and what substance this is referring to. This is moles because I was solving for the top variable here, and specifically, it's moles of HCl, since all of the numbers I put into my molarity equation pertain to the HCl. Now that I have moles of HCl, I'm ready to use the 2-to-1 ratio for my balanced equation in order to figure out the grams of MgCl2. For every 2 moles of HCl, the balanced equation tells me that I'm going to produce 1 mole of MgCl2. But I want to make sure that I have the same unit and the same substance in both of my stoichiometry problems so that I can directly compare them. That means I need to go one step further and change my moles into grams. I know that 1 mole of MgCl is equal to 95.21 grams. When I multiply everything on the top together and divide it by everything on the bottom, I get 7.1 grams of MgCl2. Remember that the limiting reactant, as soon as it runs out, it's going to stop making product. That means that the lesser number will always be the correct answer. I will only be able to produce 3.72 grams of MgCl2. It does ask me to identify the limiting reactant, and I know that the starting material that made less magnesium chloride was the magnesium. Therefore, the Mg is the limiting reactant. All right, this asks for one last part. It asks me how many liters of hydrogen gas can be produced from this reaction at 0.98 atm and 20 degrees Celsius. All right, now, these problems all connect. This is all about the same reaction. So I have already determined the limiting reactant. If I've already determined the limiting reactant, that is key, because now I know that every problem is going to start with that limiting reactant that I identified. I already know that's going to produce less product. I know that the magnesium is my limiting, so that means I care about the amount of magnesium. Always start with the limiting reactant for every stoichiometry problem that you are doing. Then the problem is asking me to determine how much H2, but specifically how many liters of H2 gas. When we are dealing with gases, remember that PV equals nRT, or our ideal gas law, is going to be very helpful. We can relate the pressure, volume, temperature, and moles of a gas using this equation. It tells me that hydrogen is a gas and that I do know the pressure is 0.98 atm. I don't know the volume, but I do know the temperature is 20 degrees Celsius. Whenever we are dealing with gas laws, we need to make sure that we convert our Celsius to Kelvin by adding 273. That is going to give me 293 Kelvin. Notice that I have P, V, and T. R is a constant, and I know that constant is always 0.0821 as long as I have a pressure in atm, volume in liters, moles, and my temperature in Kelvin. The only variable that I'm missing is N, and N represents moles, and specifically moles of the H2 gas. So if I can find moles of H2 gas, I can then use PV equals nRT to solve for the volume. I know that Mg is the limiting, so I'm always going to start with the limiting, and I can use stoichiometry to calculate the moles of H2 gas produced. I would like to use the 1-to-1 mole ratio from the balanced equation between the Mg and the H2, but I can't use that until I have moles. According to the periodic table, there are 24.31 grams in 1 mole of Mg. Now that I'm in moles of Mg, I'm ready to use that 1-to-1 mole ratio. For every 1 mole of Mg, I know that I'm going to produce 1 mole of H2. And remember that moles of H2 was what I was trying to find. If I can find moles of H2, I can then use my PV equals nRT equation to solve for volume. I know that I can produce 0.039 moles of H2. But my ultimate goal here was to get the volume, or liters, of H2 gas. I can now use my PV equals nRT equation and substitute in all of the variables that I know. I know the pressure is 0.98 atm. I don't know my volume, so I called that X. 0.039 moles. My R is a constant, 0.0821, and the temperature in Kelvin is 293. I can now solve for X, and I get 0.96 liters of H2 gas. Because I know that the mg is going to run out first, I already know that this is going to be the amount produced from my limiting. I hope this helped clear up your questions on limiting and excess reactants. Thank you for watching, and please check out my other videos.